So, Samuel, you mentioned actor-critic methods. Can you unpack how these methods improve on simple policy gradients?
Yeah, policy gradients are great, but they can be a bit unstable. Value functions, like a compass, can help stabilize that learning process.
How so? Like, what's the practical difference?
Imagine training an agent to play a game. A pure policy gradient might wiggle a lot, trying different actions. The value function acts as a baseline. It tells you how good a particular action is expected to be.
So it's like getting feedback on potential actions?
Exactly. It helps us focus on the difference between the actual action outcome and the expected action outcome, leading to more efficient learning.
And what about variance reduction? That sounds important.
Absolutely. The value function helps lower the variance in the policy gradient updates. Think of it as smoothing out those wiggles. This leads to faster and more stable learning.
So, you're saying a value function gives us better insight than just policy?
Right. It's like having a two-pronged approach. The policy finds the best actions, and the value function tells us how those actions perform, which lets us get there faster and more smoothly.
Okay, so now you're talking about deterministic policies. What's the deal with that?
Deterministic policies are simpler. They choose the same action every time in the same state. They're easier to implement, especially in continuous action spaces.
So, they're like rules?
Exactly. They don't involve random choices in that same state.
And how do you use entropy here?
Well, some methods don't use entropy in the loss function directly. They use it within the value function itself. It's like maximizing return, but also encouraging the agent to explore more diverse actions. It's an extra reward for exploration.
Interesting. And finally, you mentioned stability.
Yeah, restricting policy updates to small changes that help stabilize the whole process. This is really important in deep reinforcement learning, especially with those complex environments like pendulum, hopper, etc. Small steps are better, and they reduce the chance of getting stuck in local optima.
So, DDPG, deep deterministic policy gradient. Sounds powerful. Can you explain this, Samuel?
Sure. It's essentially a refined version of DQN, designed for continuous action spaces.
Continuous action spaces? Like controlling a robot arm?
Exactly. Think adjusting the position and angle of robot joints. Lots of possible values, not just discrete choices.
So, how does it differ from DQN?
DDPG uses a policy, a way of deciding actions, that learns to approximate the optimal action. DQN focused more on learning the value of taking specific actions.
A policy? So it's like teaching the robot how to move?
Yeah, more of a strategic guide. DDPG also uses a replay buffer, like DQN, to learn from past experiences. It trains a separate action value function and the policy.
Target networks, too? What's that about?
Yes, crucial for stability. Target networks provide a stable target for training. DDPG learns by comparing its actions to the target, kind of like calibrating a system against a fixed standard.
That's interesting. So, it's more sophisticated because it aims for optimal action instead of just action values?
Exactly. It learns a policy, a general strategy for making good decisions, in a continuous action space, unlike DQN, which works with discrete actions.
This sounds very useful. Any drawbacks?
Well, it's a bit more complex to implement than DQN, requiring more parameters and steps. Also, tuning the network can be tricky. You need to get the balance right.
So, if you had a limited budget and time, DQN might be a better choice in simpler scenarios?
Possibly. DDPG shines when you need fine-grained control in continuous environments. For example, robotics or game-playing agents controlling complex characters.
So, it's not a one-size-fits-all solution?
Absolutely not. The best choice depends on the specifics of the task. But for continuous control, DDPG might be the better option.
Okay, Samuel, you were talking about adding a policy network. Can you explain why that's crucial for this algorithm to work?
Absolutely. This algorithm, DDPG, aims to find the best action in a given situation. A policy network essentially acts as a decision-maker, choosing the optimal action based on the current state.
So it's like a strategy guide?
Exactly. It learns what actions work best in different scenarios. Crucially, This action must be continuous, not just choices between discrete actions. This continuous nature allows for smooth adjustments and learning through gradients. That's why differentiability is important.
So, if actions were discrete, learning would be harder?
Yes, you'd need a completely different learning approach if actions weren't continuous. Imagine trying to learn the best driving speed continuously, instead of just picking from a limited set of choices like slow, medium, or fast.
You mentioned using the expected Q value. Can you elaborate on that?
Sure. The Q value, in essence, estimates how good an action is in a given state. We use the policy network to get the action. Think of this as how the agent expects to perform in a given state. The expected Q value is just that prediction. On average, how well is this action going to do? We want to find the action that maximizes this expected value.
And you mentioned minimizing the negative of the objective. Why is that done?
Well, optimization algorithms frequently work better minimizing a value, and the negative just flips the objective to be minimized instead of maximized. Makes the math a little simpler in practice.
Interesting. You also mentioned using online networks, no target networks. Why the difference?
Using online networks directly speeds up learning because target networks introduce a delay. In essence, online networks learn directly from the current data, which speeds up training. Using target networks introduces a slight memory which can slow things down, and in this case, that speed advantage outweighs other potential benefits.
So, using online networks is the smart choice here for speed of learning?
Precisely. We're leveraging the current model's performance for faster updates, and in this scenario, it's a beneficial trade-off. We're not sacrificing long-term accuracy for the speed gain, which is crucial for efficiency.
Got it. You've mentioned a model optimization step. Can you break that down?
Absolutely. The code takes a batch of experiences from our replay buffer. We predict the optimal action for the next state based on our policy and value networks, and then compute the target Q value. Then we compare that target with the prediction from our current model. That difference, the error, is used to adjust the model, minimizing the loss. It's a standard backpropagation optimization approach.
That sounds like backpropagation.
Yep. It's a core component of training neural networks. Crucially, for each network update we separately optimize the policy and value networks. They aren't adjusted jointly.
Okay, so we're adjusting the policy to find the best action and the value network to estimate how good that action is. It sounds like a two-pronged approach.
Precisely. A coordinated approach to learning the best behavior.
Very clear, Samuel. This all makes sense now. Thanks for the explanation. Okay, Samuel, so we're diving deeper into TD3, right? You mentioned double learning. Can you break that down for us?
Yeah, double learning in DDPG, like in TD3, uses two separate Q-value networks.
Two separate networks? Why not just one?
Well, imagine you're trying to learn complex features in an image-based environment. Two networks might help learn faster. Think of it like having two different experts looking at the same problem. One might spot something the other misses.
So, they're mostly independent, but they share some features?
Exactly. If the environment is image-based, they could potentially share feature extraction layers, using convolutional neural networks, CNNs. That way, the CNN would extract common features. This often results in faster learning.
But you said sharing layers could be harder to train? Why is that?
Because you're combining two different learning processes, creating a potential feedback loop problem.
So, the example you gave has separate streams?
Correct. The networks are completely separate except for using the same optimizer. That's key. They use a single loss function that combines the errors from both networks.
And how does that work in practice? What's the magic sauce here?
The magic is in the twin target method. We're using target networks to calculate the targets for our value updates. The twin target considers the difference between the predicted Q value of each network and the target network. This allows both networks to learn and become more robust.
So, the target network isn't just for one Q-value network then?
No, we're using it for both. This is crucial for the stability of the algorithm. It's a common technique in reinforcement learning algorithms to improve the stability of training.
Let's look at the code snippet. You got a class FECTOC. What does this do?
This defines a fully connected neural network. It's used for approximating Q values in TD3. We're using two separate networks. Each stream takes in state and action, computes an output Q value.
So, it's two streams, separate inputs, but a combined output?
The inputs are concatenated before entering the hidden layers, but the two networks operate independently. The forward pass for both Q-value networks is distinct.
And why separate streams, even if they're using the same optimizer?
It's about redundancy and stability. Having two separate networks helps reduce the chance of getting stuck in a local optimum.
Interesting. So, it's a way to improve learning stability and potentially speed when learning complex environments.
Precisely. We're aiming to find optimal strategies in high-dimensional, often image-based, problems. That's where the advantages come in. The separation allows each network to learn and identify different aspects of the problem, resulting in a more robust overall outcome.
So, Samuel, you're saying adding noise to targets in TD3 is a form of regularization?
Yeah, Alfred. It's a clever trick. Think of it like this. Early on in training, the Q functions might incorrectly value certain actions. That noise helps spread the value estimations across a wider range of actions, forcing the policy network to be more robust and less prone to getting stuck on poor local optima.
So, how exactly does this noise get added to the target? Can you give us a specific example?
We use clipped Gaussian noise. Basically, we randomly sample a value from a Gaussian distribution. But importantly, we keep that noise within a specific range, a minimum and a maximum.
Why do we clamp the noise?
To keep the actions within the allowed bounds of the environment. You don't want to try to execute an action that's physically impossible.
Got it. And this smoothing happens during the model optimization?
Precisely. During the optimization step, we sample this noise, add it to the action predicted by our target policy network, and then clamp that noisy action to stay within the environment's limits.
Can you explain this a bit more? How does that translate into the code you showed earlier?
Right. The code calculates the range of actions possible. Then, it generates noise within a specified ratio of that range. Crucially, it keeps this noise within a minimum and maximum value. It then adds this clipped noise to the output of the target policy. And finally, it clips the result back into the permissible action range of the environment.
That makes sense. So, it's not just adding random noise. It's carefully controlling it?
Precisely. The clamping is crucial for keeping the actions feasible.
I'm getting a feel for this. But, you mentioned something about delayed policy updates? Is that related to how often we update the policy?
Absolutely. We update the policy less frequently than the value network. This is a key difference, and it's often important in stable reinforcement learning. This helps in the exploration-exploitation trade-off of reinforcement learning, meaning it allows the algorithm to have a better sense of the environment's reward structure before making major policy changes.
That sounds quite nuanced. It's fascinating how carefully this whole process is managed, right?
Yes, precisely. It's a technique that helps maintain a balance between exploration and exploitation. The delayed updates help the agent understand the overall structure of rewards before making adjustments.
Great explanation, Samuel. This is all really helpful. Okay, Samuel, you were talking about TD3 and delaying updates. Can you unpack that a bit more? Why is this delay helpful?
Yeah, delaying updates is key. Imagine training a model to predict something, like, say, the stock market. Initially, the model might get things wrong, but it learns. So if we update the prediction algorithm too quickly, we're letting initial mistakes drive the next steps. Slowing it down lets the model get more accurate, more settled before taking actions based on it.
So, it's like letting the value function settle down? Makes sense.
Exactly. The online Q function, that's like the core learning engine, is changing rapidly at first. It's like a wild, fast-moving river. If the policy, the actions, updates too quickly, it gets swept away by those initial inaccuracies. Delaying the policy gives the Q function time to smooth out its predictions.
And you're recommending updating the policy every other update to the Q function. Is that always the best?
Well, that's a good rule of thumb, Alfred. It's not always going to be the optimal delay, though. It's often a good starting point. You might need to tweak that based on specific tasks. But in this particular case, it seems to work pretty well for the Hopper robot.
Why one stream of the online value model for the action?
It's for efficiency. Using one stream, even if it's the same stream every time, simplifies the process. It's like choosing one lane to get through traffic rather than switching between different lanes in every step. It might not be the absolute perfect approach, but it strikes a balance between complexity and effectiveness.
And this is different from DDPG?
Absolutely. TD3 is an improvement. It addresses a crucial flaw in DDPG, which is that it doesn't properly address the error caused by learning the values. By slowing the policy updates, you improve the performance of TD3.
Interesting. So, this is a balancing act between speed and accuracy?
Precisely. You want to learn quickly, but you also need to ensure the learning is reliable. The delay gives us that stability. It's a common pattern in machine learning, isn't it?
Yeah, absolutely. Thanks for that explanation. We'll circle back to the other specifics later. Okay, Samuel, so we're talking about this thing called SAC, right? It's about maximizing something? Entropy?
Yeah, exactly. SAC, or Soft Actor-Critic, is a reinforcement learning algorithm. It's special because it adds entropy to the Bellman equation.
Entropy? Like information theory entropy? What's that doing in reinforcement learning?
Right. It's about encouraging exploration. Imagine an agent trying to find the best path. If it's too focused on maximizing reward, it might get stuck in a local optimum. It might always choose the same action, even if there are other potentially better options.
So, adding entropy helps it explore more?
Precisely. By including entropy in the value function, we're incentivizing the agent to try different actions. It's a way to balance exploration and exploitation. Find the best possible path, but also try new paths.
Makes sense. So, this entropy term, how does it work mathematically?
Well, we're adding the expected entropy of the next policy to the reward. Think of it as a bonus for trying new things. And importantly, a parameter alpha tunes how much weight we give to this entropy.
So, higher alpha means more emphasis on exploration?
Exactly. A smaller alpha makes the agent focus more on immediate reward. Higher alpha means it's more willing to explore even if it means a slightly lower reward in the short term. It's a critical balance to get right.
And in practice, how does this work? Imagine a robot trying to navigate a maze. How does adding this entropy help it?
Imagine a robot navigating a maze. If it only maximizes the reward, finding the shortest path, it might miss other quicker shortcuts hidden in less traveled parts of the maze. Entropy pushes it to explore those areas, even if it means taking a longer path sometimes. It could find shortcuts hidden in less obvious places.
So, it's like a reward for exploration?
That's one way to think about it. It's balancing the desire to maximize reward with the need to explore new options. Finding the sweet spot for alpha, it's a delicate tuning process.
Right, makes perfect sense. I'm starting to get it. Okay, Samuel, we're diving into automatic tuning for SAC. Can you unpack what's special about adjusting the entropy coefficient, alpha, automatically?
Yeah, Alfred. This automatic tuning is a big plus. Normally, you'd have to fiddle with hyperparameters to control exploration-exploitation trade-offs. But with SAC, the algorithm figures out the right entropy level.
So, it learns the best level of randomness, basically?
Precisely. It's learning the optimal exploration strategy. We use a heuristic target entropy to guide that process.
How's the heuristic derived? Any tricks there?
It's based on the action space's shape. The target entropy is essentially the negative product of the action space dimensions. Think of it as a natural starting point. It's quite clever because it relates to the complexity of actions.
So, if the action space is a simpler thing, say 1D, the entropy is less?
Yes, exactly. A smaller action space naturally implies less need for exploration.
And the algorithm tunes alpha to match this target entropy?
That's right. The algorithm optimizes alpha so the entropy term is effectively taken care of. You get virtually no hyperparameters to tweak manually.
Neat. Now let's peek at the code. What role does the function self.target_entropy equals mp.prod self.env_max.shape play?
That line calculates the target entropy. It figures out what entropy level the agent should ideally maintain, using the dimensions of the environment's maximum action space. It's crucial for automatically adjusting alpha.
And how does the alpha underscore loss equals dash self.policy underscore model dot log alpha asterisk target underscore alpha mean function work?
This is the core of the automatic tuning mechanism. It measures how well the current alpha value aligns with the target entropy. The loss function is designed to minimize this discrepancy.
So, it's a balancing act between encouraging a level of randomness and keeping the algorithm focused on the task.
Exactly. By tweaking alpha, the algorithm maintains the correct balance. Less randomness leads to faster convergence, but too little randomness limits exploration and potentially hinders finding optimal solutions. The algorithm automatically discovers this balance, which is super helpful for training time.
Makes sense. So, why is torch.in.utils.clip underscore grad underscore norm underscore important in the optimization steps?
It prevents the gradients from exploding. Gradient clipping is a crucial technique for stability in training deep learning models. Without it, gradients can sometimes become so large that they destabilize the training process and make it much harder to converge.
Any potential pitfalls or issues with this automatic tuning?
One potential concern is that the heuristic might not always be perfect. The optimal entropy might depend on other factors, and it's based on the dimensions of the action space. This means the agent may have to make small adjustments over time based on the complexity of the learning environment.
Excellent points. So, in essence, SSE leverages automatic entropy tuning to make it easier for users and provide a more stable and effective training process for reinforcement learning algorithms.
Yes, that's a good summary. The automatic tuning simplifies the learning process significantly.
Okay, Samuel. So you're saying PPO is an improvement on A2C? What makes it better?
Yeah, exactly. It builds on A2C, but it's got some key improvements. One big one is how it handles experience.
Interesting. How so?
Well, imagine you're training a robot to walk. A 2C might only use each experience once. PPO, though, can reuse those experiences. That's pretty cool.
So, it's like a learning from mistakes kind of thing?
Precisely. And it does it efficiently. Instead of having to do one big training session on all the data, PPO uses a replay buffer.
A replay buffer? Like a video game replay?
Sort of. It's a storage space for all the collected experience data. Every time the robot takes a step, the data goes into the buffer. Then, when it's time to train, PPO randomly samples from this buffer.
So, it's like a random selection of the experiences?
Exactly. It gets a mini batch of experiences, which is a smaller subset of the entire data. And that's key.
Why is that important?
Because it introduces randomness into the training process, even though you're reusing the experiences. And you're learning from diverse experiences, not just a fixed sequence.
And how does this replay buffer translate to better results for the robot?
Well, it's more stable learning. It's like getting multiple perspectives on how the robot should move in those scenarios. A mini-batch has less risk of getting stuck in a bad local minimum during training.
So, you're saying PPO is better than A2C in terms of efficiency and generalizability?
Absolutely, because you can learn from many experiences repeatedly. Plus, it uses Generalized Advantage Estimation, GAE, for policy targets, which is another way to improve stability and efficiency.
Can you explain GAE a bit?
Sure. GAE is a way to estimate the advantage of an action. It basically predicts how good an action is compared to others in the context of an episode.
How does that help in the robot training process?
By having a better estimate of advantage, the algorithm can make better choices and update the policy more accurately. This reduces the variance in the learning process.
That's interesting. So, the replay buffer, along with GAE, is the core of this PPO efficiency.
That's correct. That's why PPO is considered an upgrade over A2C.
Okay, I see. So, you've given us a solid overview of the core concepts.
Correct.
Now let's dive into the code example you've got there. Can you walk us through what this code snippet does conceptually?
Absolutely.
So, Samuel, we're talking about clipping value functions. Can you explain how this works in practice?
Sure, Alfred. Clipping value function updates is a technique to control how much Q-values can change during training. Imagine you're adjusting a complex system, and you don't want massive jumps in performance from one step to the next.
Right. So it's about controlling the variance in the values?
Exactly. It keeps changes smooth, regardless if adjustments to parameters are big or small. You want performance to gradually improve, not have sudden swings.
So you're essentially limiting how much the value function can change at each step?
Exactly. We're setting limits to those parameter space adjustments. It's like saying, okay, the value can go this much higher, but not more than this. This technique helps stabilize learning. That makes the algorithm more robust to noisy or unstable data in the environment.
Okay, and you mentioned sampling from a replay buffer. How does that work in conjunction with clipping?
We sample from the replay buffer to get the necessary values for updating the value function. Then we calculate the predicted values compared to the returns, which is the target value. We take the magnitude of the two errors and clip the difference within a specific range. Think of it as saying, hey, this much difference is okay, but not more.
So you're doing a kind of error correction, but with a constraint?
Exactly. We move the predicted values, clip the difference, and then adjust it back to keep it within that range. The code shows how to sample, then clip the error in a predictable, stable way, ensuring smooth value function updates.
Okay, that makes sense. But what's the practical benefit of all this?
Well, in reinforcement learning, getting stable, smooth value function updates is a huge deal. It often helps prevent oscillations and getting stuck in local minima during training. It leads to more stable and efficient training, with more consistent improvements. It's about building a strong foundation.
And you mentioned PPO optimization? How does clipping come into play there?
In PPO, clipping is directly applied to the policy objective calculation. This ensures that the policy updates are constrained. The code demonstrates the logic clearly. Think of clipping like putting brakes on how much a learning algorithm can adjust its policy in one step.
So you clip the policy ratio.
Yes. We calculate the objective and a clipped objective. The final loss function for the policy uses the minimum of the two, thus clipping the values in that range to make sure we have a controlled update.
Great, Samuel. This helps the model learn better and makes it more stable. Thanks for explaining that. Okay, Samuel, we've covered DDPG and TD3. What's the core difference between those and SAC?
DDPG and TD3 are deterministic. They learn policies that pick a single action. SAC, on the other hand, is stochastic.
Stochastic? What does that mean?
It learns a probability distribution of actions. Instead of choosing just one action, it chooses from a range of possibilities. Think of it like gambling. You don't just win or lose, you have a chance of different outcomes.
So, why is that a big deal in reinforcement learning?
It's better for exploration. Deterministic policies can get stuck in local optima. Stochastic policies allow for more varied exploration, more likely finding better solutions.
How does that exploration work?
The exploration is built right into the policy. It's not something separate you have to add.
And what about PPO?
PPO, or proximal policy optimization, is a non-policy method. It's like a more cautious version of A2C.
A 2C?
Advantage Actor-Critic. It's another powerful RL algorithm. PPO learns by updating the policy based on recent experiences, using a clipped objective function. It makes the policy improvements more stable and less prone to big swings.
So, PPO is better for stability?
Exactly. It's more robust in real-world situations, often outperforming others when the learning environment is noisy or there's high variance. But it's not as flexible as SAC. SAC has the upside of possibly finding better outcomes, but might be more sensitive to the specific environment.
Interesting. So, each algorithm has strengths and weaknesses. What do you think the next frontier of research is in deep reinforcement learning, especially considering this field's ties to AI?
Absolutely. We're moving toward creating systems that are more adaptable and general. That's where AI goes to understand human intelligence.
Can you give me an example?
Imagine an agent that can learn to play a diverse range of games, not just one type. That's a step towards true general intelligence. Or an AI that can assist in complex problem solving, for example in financial modeling or scientific discovery.
That's impressive. Thanks, Samuel. That was really helpful.